Hello everyone, my name is Sana Alamgir and I am PhD candidate at University of Brasilia, Brazil. My work is supervised by Professor Dr. Mileni and she is an outstanding professor. Name of my computer laboratory is Group of Digital Signal Processing. This lab consists of a large number of people who are working on digital signal processing in different domains. I'm going to talk about visual quality assessment of multimedia based on machine learning. I also aim to give a glance at some of the mathematical notations that has helped us to design accurate algorithms of visual quality assessment in this journey. First, I will briefly describe what are two-dimensional images and videos and what do we mean by their processing. Also, what are four-dimensional images and their processing, and under four-dimensional images, I will cover light field images. Then I will describe in detail what are quality assessment and their methods, and these methods will be based on machine learning or deep learning techniques. Then I will describe what is visual attention and what is its role in quality assessment. Then I will conclude this talk with a briefing or summary. We denote images by two-dimensional functions of the form f of x, y. This image shows an example of a common imaging system, and in this case, this imaging system is composed of two-dimensional grid of sensors. Energy of illumination source is reflected by scene, and every sensor inside this two-dimensional grid captures this energy and plots it onto image plane. And inside this image plane, the illumination is represented as analog signal, where every value is a continuous number. Then after using some specific imaging software, this analog signal is converted into digital signal where the illumination is converted into digitized image. So in this digitized image, now the illumination is represented by a discrete number. Once we obtain our digital image, we can mathematically represent it in a traditional matrix form. Given that capital M is the total number of rows and capital N is the total number of columns, we can represent this two-dimensional image in this complete matrix format. Each element in this format is called pixel, and the entire matrix is called spatial domain of the two-dimensional image. And this spatial domain gives us information about pixel values of the corresponding two-dimensional image. From now on, I will use the word pixels to represent each element value inside images. If we take this two-dimensional image, the origin of this image is represented by the first element, and we call this element by f of 0 and 0, and the next element under the same row will be represented as f of 0 and 1. Imagine we play hundreds of two-dimensional images in a sequence and over a given time frame. This phenomena gives us a two-dimensional video that is composed of these hundreds of two-dimensional images. To define two-dimensional videos technically, it is a program, movie, or other visual media product that features moving images, and it can be with or without audio. For example, this is a two-dimensional video that has been taken from Convid1K database, and this is a list of two-dimensional images that this video is composed of. Remember that the sequence of two-dimensional image is very important to show the moving object as they were captured. And for the video, each two-dimensional image is called its frame. So the first image in a sequence is called frame 1, second image in a sequence is called frame 2, and so on. Another term that always comes with two-dimensional videos is frames per second, and the acronym we often use is FPS, and it is a frequency or rate at which the consecutive images are captured or displayed in the video. So the higher FPS we keep, smoother and high resolution videos we can get. Now we know what are two-dimensional images and videos. Next, let's see what do we mean by their processing. And by processing, we mean to perform some operations on 2D images or videos inside a digital computer. And we can specify these operations if we know our knowledge base. And in knowledge base, we can specify two things. What is our problem that we are going to solve, and what are the types of images? Are these satellite images or the images of animals or any other objects? And the problem can be related to detailing regions or detecting information of interest. So if we know our database, and the problem, we can specify our operations. Let me give you an example of very popular application that is called Adobe Photoshop, and you might know what type of operations you can perform on 2D images or videos using this application. Now you can get a clear idea what are these operations and what do we mean by processing digital images or videos. After two-dimensional images and videos, now we are in the era where the immersive media has become very popular. And in immersive media, one of the multimedia content is 4D light field image that has gained the attraction of research community recently. A light field image can be captured using four-dimensional imaging system, and four-dimensional imaging system captures light rays from every direction. This is an example of a 4D light field image camera, and it is called Litro Ilum. This is very basic camera, but now we have latest camera that has a grid of micro lenses, but I will not go into its detail. Let's focus on this Litro Ilum 4D light field image camera, and this image shows the organization of imaging system that this camera uses. So as you can see in this image, between sensor and main lens, there is a list of micro lenses, and each micro lens captures the scene with different direction and different focus. So depending on the number of these micro lenses, we can get sub views, multi views, or sub aperture images with different focus. And by combining all of these sub views, we can get all focus image. So the reason of the popularity of 4D light field images is that we can change the focus in each subview even after the image is captured. We can represent mathematically a 4D light field image using planoptic function that is parameterized by four coordinates u, v, and st. As you can see in this image, we have u, v, and st planes. So UV plane gives angular and spatial information of a light field image, and you can see that inside UV plane a two-dimensional grid of all subviews is displayed, and the resolution of each single view is represented by the coordinates s and t. So UV and ST are two different representations of a light field image. Another representation of a light field image is epipolar plane images. These images are used by drawing epipolar lines over UV plane. Specifically, if we fix V and T coordinates, we can get horizontal EPI or epipolar plane image, whereas by focusing S and T coordinates, we can obtain vertical EPI image. In EPIs, slopes of lines gives information about depth and geometry of a light field image. So if there is a disturbance in the pixel values of a light field image, the lines in EPIs are also disturbed. So EPI formation of light field image is widely used in different target domains of light field image processing. Now that we know what are two-dimensional images videos and what are four-dimensional images, next let's see what are the challenges that we face during the processing of this multimedia content. Let's take an example of 2D media content first. Starting from the acquisition and display, you can see that the image or video has to go through several stages. And for example, if the storage is not sufficient to keep the processing media, this media has to be compressed to reduce its size to fulfill the requirement of the storage. And once it is transmitted over the network, it starts traveling from device to device, and every device has different requirements for display. And to fulfill those requirements, the software of these devices alter the pixel values of the media content, and in this scenario, this content loses its original quality. General purpose processing system of 4D light field images is slightly different because 4D light field image is captured in different format. Therefore, after it is captured, it is represented in different formats, and then because it contains a huge metadata, to reduce its size, it is encoded or compressed, transmitted over the internet, or kept in a storage, and then decompressed it so that it can be displayed in any device. So you can see that 4D light field has to go through many stages more than two-dimensional media content. So it is possible that in any of these stages, this 4D media will lose its original quality. So let's take an example of what do I mean by losing the original quality. So this is a frame which is reference frame and it is in its original quality and it does not have any kind of disturbance in its pixel values. So when it is transmitted over the internet and somehow by applying different kind of softwares for display or compression, the pixel values are transformed or lost. Let's take an example of these JPEG, JPEG 2K, JPEG TE and JPEG 2K TE. These are compression algorithms that are used to reduce their sizes. You can see a lot of important information around the faces have been lost and we cannot recognize each object individually. So it means that these images have lost their original quality. Let's take another example of these color related distortions, CCCCS, and we can see that the colors are lost, giving us more grayish output. When this media travels over the internet and lands on any end user devices, how do we know that the media is fulfilling the end user requirement? Or how do we know that the amount of distortion is bearable or not? To quantify that, here we need visual quality assessment methods. Let me give you an example of Netflix, which is very popular video streaming application and it is highly demanded to deliver its videos consuming less bandwidth and less data. And Netflix does that by compressing the videos using different compression techniques. And when this compressed data is received by the end user, Netflix quantifies the amount of distortion. It uses its video multi-method assessment fusion quality assessment method. It is the reason that no matter you are using low bandwidth or smaller devices with less data, you can have a buffer-free experience of video streaming. And you can also experience high resolution videos by consuming less bandwidth. Now we know what are quality assessment methods. Next, we look deeper into different types of quality assessment methods. And before that, let's first define what is quality assessment to put it in a one-liner. The goal of quality assessment method is to calculate the extent of degradation, or in other words, we can say that up to what extent the degraded or distorted content is satisfying the end user requirements. Multimedia applications such as Netflix assess the visual quality of the affected visual content to make sure that the delivered content meets the requirements of end users. So it is now clear that why we need visual quality assessment methods. Now let's look at different types of quality assessment methods. One type of quality assessment method is subjective quality assessment. This involves a psychophysical experiment and where a group of people evaluates the quality of every test content and assigns a score based on its quality. And at the end, all of these scores are averaged to generate mean opinion score or MOS for that test content. And this MOS score is used as a ground truth in quality assessment. Now the problem is that according to the current Cisco report, every second global internet traffic is increased by 100,000 gigabytes and 82% of this traffic is composed of videos. So in this scenario, the subjective experiment becomes unfeasible. It is expensive, time consuming, and it is not easily repeated. So to assess the quality of distorted visual content fast and without human intervention, we use objective quality assessment. So these are basically algorithms that run on computer and predict the quality of distorted visual content. These methods are fast and feasible in real world applications. So after developing a quality assessment method, how do we know that how good the predicted quality is? To quantify the efficiency of our quality assessment methods, we compare these predicted quality scores with the ground truths MOS that we obtained in subjective quality assessment. And we perform these comparisons using different kinds of algorithms. And I will tell you about those algorithms later. There are different categories of objective quality assessment depending on the reference information used. For example, if the method uses the information from both reference input and its distorted version or test input, the method is called full reference assessment method. But if the method uses 100% information from test input and partial information from its reference input, the method is called reduced reference quality assessment method. But if method is only dependent on test content and knows nothing about its reference, the method is called no reference or blind quality assessment algorithm. And to evaluate the performance of quality assessment methods, as I told you before, there are some algorithms that we use. These algorithms are called performance evaluation metrics. And Spearman's rank order correlation coefficient, Pearson's linear correlation coefficient are two of the performance evaluation metrics that are most common and widely used. SROCC evaluates the performance between two variables by analyzing the monotonic relationship, while PLCC evaluates the performance by analyzing the linear relationship. So for both SROCC and PLCC, N represents the total number of observations, and XI is the ith representation of X, and yi is the ith representation of y. In PLCC, d of I represents the difference between xi and y of I. Both SRCC and PLCC generates a scalar output that is a number between 0 and 1. If the number is closer to 1, the correlation is considered to be very good, which represents that the predicted quality score is in agreement with the human judgment or MOS. Recently, to design quality assessment methods, machine learning and deep learning approaches have become very popular. Machine learning is defined by Upledon in his book Introduction to Machine Learning, where he says that machine learning represents the algorithms that process the data, learn from that data, and then apply what they have learned to make decisions. And inside this image, you can see that the machine learning is subdomain of artificial intelligence, where the deep learning is the subdomain of machine learning. And with the help of mathematical linear algebra, matrices, and vectors calculators, we can build several machine learning methods as mentioned in this graph. On the other hand, deep learning consists of neural networks, and these neural networks are inspired by the way the information is processed by the neurons in human brain. This image shows general architecture of a neural network, which is composed of three basic layers. First one is input layer, where we define our input. The hidden layer represents the feature extraction, and it can contain one layer of neural network or multiple layers of neural network. And the final layer is the output layer, where we get our output. And to apply the deep learning approach, we can use multi-layer perceptron, convolution neural network, and long short-term memory network. Before we know what is the importance of visual attention in quality assessment, first, let me give you a brief introduction of what is visual attention. So visual attention is a mechanism of human visual system. When observing a scene, the human eye filters a large amount of visual information available by focusing on selected regions. And these selected regions are called salient regions. For example, in these images, you can see that the highlighted regions are referred as silent regions because these have brighter colors or have text and faces. And also the moving objects in videos attract the human visual system most. And the algorithms or metrics that detect silent regions automatically without human intervention are called saliency models. Now, why we are discussing visual attention in the topic of visual quality assessment. For example, if I show you a picture that has face or a text and I ask you to look at it and recognize it or read the text, but the region around text or face or the region of interest is distorted and you cannot describe it or read the text, you will feel annoyed. So in visual quality assessment, we believe that the regions that are attracted to human visual system should be treated differently while assessing their quality. Therefore, to do that, we use saliency models to predict the silent regions and then pass this saliency information to visual quality assessment methods for better quality predictions. So to incorporate the saliency information inside visual attention quality assessment methods, there are two basic ways. The first way is that quality assessment methods are designed to capture the features that are relevant to human visual systems. For example, texture in image, bright colors, luminance, and contrast features. Another way is we incorporate the silent features by weighting the special features with it and then pass these weighted features to quality metrics which are processed for final quality predictions. So this image shows diagrammatical explanation of second method of incorporating saliency map inside our special features. We can use this mathematical notation to weight the saliency information. This is the special features. We take its sum, multiply it with saliency information and then divide it with the overall saliency information. So that's how we obtain the weighted features. Keeping in mind the importance of incorporating saliency information for better quality predictions, we developed a quality assessment of two-dimensional images and it is called multi-scale salient local binary patterns. So MSLBP is a general purpose, which means that it can work on different environment with different types of distortions. The foundation of this method is based on MLBP, which is multi-scale local binary pattern algorithm. And MLBP is based on local binary pattern algorithm that works as shown in this picture. Let's take an example of 3 by 3 block of image. The parameters that LBP uses to extract the basic features are radius and number of neighboring pixels. So for now, we have specified the radius 1. It defines the distance between the center pixel and its neighboring pixel. So the distance here we have specified is 1 pixel and the neighboring pixels are 8. To define the LBP feature for center pixel value 35, we perform the LBP metric over it. First, we take the difference between neighboring pixel value and the center pixel value. If the difference is greater than or equal to 0, we represent the output in binary code as 1. Otherwise, we represent the difference as 0. So the 0 circle represents the output 1 and the black circle represent the output 0 in binary code. Next, we organize this binary code in a vector format based on their position of each pixel output. Next, we convert this binary code into decimal format, and by summing up all the pixel values that we obtained from decimal conversion, we get the output 13 that is used to represent the center pixel 35. This is the example of LBP, the foundation of MLBP. How we get MLBP is that we use every possible value of radius and neighboring pixels for our test images. In other words, using the multiple values of radius and neighboring pixels, we get multi-scale local binary patterns. This image shows a representation of MLBP. Using these MLBPs, we get our silent local binary patterns. First column shows our distorted input images. Second column shows their silency maps. These columns shows the MLBP maps that we obtained using radius 1 and 2, and for radius 1 we used neighboring pixels 4 and 8, but for radius 2 we used neighboring pixels 4, 8 and 16. Next, we weighted each of these MLBP map with the silency information, and this way we obtained silent local binary patterns. To obtain the silency map for every distorted input, we used Boolean map silency model. Now, because we have obtained our weighted silent local binary patterns, next we are going to generate histograms of each of these SLBPs. SLBP histograms are concatenated to produce a feature vector for each image. So the plus operator represents the concatenation, and by concatenating all of the SLBPs for one input, we get a feature vector that represents its corresponding distorted image. Next, after obtaining our feature vector for every input image, we supplied these feature vectors to a random forest regressor algorithm. It is a machine learning based algorithm, and we trained this regressor to predict the quality. Figure A and B represents the final results for a dataset of distorted images live and CSIQ. So to represent the final results, we have used violin plots. These plots are very good to see the distribution of all predictions over corresponding quality assessment methods. In each of the plot, the first column shows our proposed method and the performance we have compared with other comparison quality assessment methods. So as you can see that the mean value obtained by the proposed method is higher than the rest of the comparison matrix for both datasets. We also developed a quality assessment method to assess the quality of distorted two-dimensional videos. So this method is based on CNN and it is no reference, which means it uses no information from reference videos, and it is based on temporal and spatial silency patch selection procedure. So in video quality assessment, we obtain the ground truth subjective quality scores for each video. But for our method, we wanted to have ground truth subjective score of each frame because there is a lack of dataset that offers subjective scores of frames. So in this method, we generated custom target quality scores to train the CNN for each video frame. In this method, because we are going to use spatial and temporal features, first let's define what are spatial or temporal features and how did we obtain them. As I told you before in the section of introduction that spatial domain belongs to the pixel values and it gives us information about pixels. So if we want to define features that are related to textures, resolutions, and contrast values, color values, we use spatial domain to extract pixel values related features. And similarly, if we say that we are going to use spatial saliency, it means that the saliency information will be related to the pixels or will be generated based on the pixel formation. And in this method, we generated saliency maps using a saliency model called SDSP, which is short form of saliency detection method by combining simple priors. In this image, you can see the examples of spatial saliency maps that we generated from input frames of distorted videos. To show these images, we randomly selected one frame from distorted video and generated a saliency map of this frame. Next, we use temporal saliency, but let's look at what are temporal features. Temporal refers to time. Every time we say temporal, it is always referring some features that are running over a time, and every time the features are changing. So, temporal characterization occurs when we have a series of images occurring at different time in a given time lapse. In the introduction of videos, as I showed you an example of video and its number of frames or our time lapse. So these number of frames are acting as a temporal feature for corresponding video. And the temporal saliency will be the saliency information that is related to time frame or time lapse of the frames. Why we are going for temporal saliency? Because in human visual system, moving objects also attract the most. So they attract the viewer's attention, selective behavior in a temporal domain. We see that how we obtain these special saliency maps And next, to obtain the temporal silencing maps, we used optical flow maps. Optical flow is the pattern of apparent motion of image objects between two consecutive frames caused by the movement of either object or camera. And the result of optical flow algorithm is a 2D vector where each vector is a displacement vector showing the movement of points from first frame to second and so on. This is the example of video that has one object moving around under sea, and you can see that the obtained optical flow maps between each frame are different because of the movement is changing in every frame. If the pixels in the optical flow maps are bright, it means that the object is near to the camera. The optical flow of first frame is always a blank frame because first frame does not show any movement. But if we compare the first frame with second frame, it represents a 2D vector field of motion vectors that represent the motion from first frame to the second frame. So this image shows a complete example of spatial saliency maps and temporal saliency maps. So again, the first column shows the randomly selected frame from distorted video, and the second column shows saliency maps, and the third column shows optical flow maps of every input frame. So you can see that the cloud looking like texture represents the motion vectors with its direction. And this cloud like texture appears with respect to the movement of object in the video. To obtain this optical flow map, the frame was compared with its next consecutive frame. The key point of this 2D video quality assessment method is that it is light because we have used videos with only 2 FPS. In other words, we have downsampled videos to contain 2 FPS frames in a given time. So in quality assessment, every video dataset comes with a detail of its total number of seconds and in each second how many frames are being displayed. Using that information, we can always downsample a video with the following approach. To downsample a video, the algorithm basically states as follows. If we know a total number of frames and duration of the video, we can divide number of frames by duration. For example, if there are 8 seconds in the video in total, we can create a chunk of every second. And then the next thing we need to know what is the FPS rate or what are the number of frames that in every second are being displayed. Then we fill every chunk of a second with its number of frames, and every consecutive chunk will start the indexing of frames from the number next where the previous chunk was ended. And this way, in each chunk, we can randomly select indexes of selected number of frames. For example, in this case, we wanted to use 2 FPS, so in every chunk of every second, we selected 2 random indexes of the frames. We use no reference two-dimensional image quality metric to assign a custom quality score to each frame, and we saved it to train our CNN later. Next, we generated spatial saliency using saliency model, and then we extracted temporal saliency using optical flow maps. And then for each spatial and temporal saliency map, we divided these maps into 32 by 32 patches. Next, we weight each of the patch and obtained a weight for each patch. Next, based on their weights, we sorted all of the patches in descending order. Then out of these patches, we selected a certain percentage of patches. This image shows an example of selected number of patches, which is 216. So from this input image, we selected top weighted 216 patches and the final output looks like this. And to represent this process mathematically, SSPK shows special saliency of patch K and TSPK shows temporal saliency of patch K. Next, to obtain weighted patch, we multiplied the SS of PK with alpha and multiplied TS of PK with 1 minus alpha and finally summed up their answers to get weighted batch. To train the CNN, we used the prepared custom quality targets for each frame, and instead of processing entire frame, we selected the top weighted patches and fed them to a CNN for final quality predictions. In the end, to predict the final quality, we used this mathematical notation, which describes the process of computing the final quality score of input frame. So this is the predicted this represents predicted quality score of this represents the predicted quality score of all patches for a corresponding input frame, which is multiplied by the weight we computed previously and then divided by the same weight. And in this table, we can see the final results in the format of SRCC and PLCC values. Last column shows the results obtained by our method for video quality datasets CSIQ and live, and the bold values represent the highest values in comparison of each row. And we can see that for most of the cases, proposed method has obtained the highest PLCC and SRCC correlations. Now let's conclude the talk. Despite of the progress in development of quality assessment methods, we still have some challenges to overcome. For example, if one quality assessment is trained for one quality data set that is distorted with certain number of distortions, and if we test the same model for another scenario in terms of different resolution, color information, and different types of distortions, the quality assessment method might not work. To overcome these challenges, we need to develop more robust, consistent, and accurate quality assessment methods. And to do that, we need mathematicians because they know how to use abstract language, work with algorithms, self analyze their computational thinking, and accurately modeling real world solutions. And finally, we believe that great mathematicians have potential to become great computer scientists. Before I start taking questions from the audience, I want to thank 7th International Research Forum Echoes of Science and Technology for inviting me and giving me the opportunity to present my work and motivate the students of this institute to come forward and join the computer science field for their higher studies. Thank you very much.